Good morning everyone! Welcome to our video presentation. And today we will be exploring one of Southeast Asia's most geologically significant feature, the Barisan Metamorphic Belt of Sumatra. A deeply buried record of ancient plate collision that stretched over 1,650 kilometers along the western edge of the island. Using our research poster as a visual guide, we will walk you through the belt's location and geological setting, the rocks it is made of, the evidence preserved in mineral, and how it formed through oblique subduction, and why it matters for both Indonesian geology and global science. So, let's begin! But before that, let me introduce myself. My name is Keisha Naila Bilbina Suprapto, and today I would like to tell you about the location and geological setting of Barisan Metamorphic Rock, Sumatra. So, let's orient ourselves. If you look at the left side of the poster, you will see two maps. The first shows Indonesian map, and the red shaded corridor along the west coast of Sumatra marks the Barisan Metamorphic Belt. And the second maps give us more detail. The belt sits at the boundary between the Sundaland block, which is part of the Eurasian Plate, and the zone where the Indo-Australian Plate puts underneath it. Think of it like the crumbled zone of a car crash, set on a continental scale and over hundreds of millions of years. The belt forms part of the geology called the Sundaland basement. Ancient rock that were cooked and squeezed deep the underground and then slowly exhumed or lifted to the surface over geological time. This tectonic shifting is what makes the Barisan Belt so scientifically valuable. It is a window into ancient subduction process that we cannot directly observe today.
Okay, let's move to the next section. Here I will explain about the basement lithology and petrological evidence. Now, let's look at what the belt is actually made of. The basement lithology here, that is the suite of rock types, can be grouped into three broad categories. First, we have the metamorphic rocks here, schist, gneiss, marble, and quartzite. These are the dominant rock types and are associated with Tarantam Formation, which dates back to the Carboniferous period, roughly 300 to 360 million years ago. Second one, we have igneous rocks, specifically S-type granites and pegmatites of Jurassic age. These were intruded into the metamorphic rocks as molten material rose from the deep crust. And third, and perhaps the most exciting for geologists, here we have oceanic rocks. Found only locally, these include serpentinite, pillow basalt, gabbro, and chert, remnants of ancient ocean floor that were trapped and preserved during the collision process. These are called ophiolites, and their presence here is the key evidence of past subduction. The important minerals detected across these rocks include quartz, feldspar, mica, garnet, pyroxene, and titanomagnetite, the main magnetic carrier, as well as goethite, a weathering product found in survey samples. Okay, that is for basement lithology, and we move to petrological evidence. We have mineral assemblage and metamorphic facies here. From petrological evidence, rocks don't just tell us what was there, they tell us the conditions under which they formed. This is where petrology, the study of rocks, become very, very powerful. Looking at the mineral assemblage here, in the poster, each rock type carries a signature collection of minerals. For example, schist contain muscovite, biotite, quartz, chlorite, and garnet. Gneiss contain quartz, feldspar, biotite, and muscovite. These specific combinations tell us the temperature and pressure conditions under which the rocks were metamorphosed. And here, on the metamorphic facies, the PT diagram or pressure temperature diagram on the poster places peak metamorphism at 500 to 650 degrees Celsius and 5 to 8 kilobars of pressure. That corresponds to the amphibolite facies, meaning these rocks were buried approximately around 15 to 25 kilometers underground before being exhumed. And to put it in the perspective, that is like burying a rock beneath 70 to 90 Empire State Buildings stacked on the top of each other. The granite found in the belt is classified as S-type and paraluminous, meaning it originated from partial melting of sedimentary or maybe meta-sedimentary source rocks. This is confirmed by the geochemical spider diagram here in the poster, which shows patterns consistent with arc-related magmatism and crustal melting, not from a mantle source. Together, these petrological clues paint a picture of deep burial, intense metamorphism, and eventual uplift, a complete metamorphic cycle recorded in rock. Next, my friend Fajar will present on the tectonic interpretation. Thank you.
Now, I will explain the tectonic interpretation of the Barisan Metamorphic Belt. This belt represents the exposed basement of Sundaland, formed by long-term oblique subduction of the Indo-Australian Plate. It records a long tectonic history from Paleozoic to Cenozoic, including subduction, accretion, and metamorphism. In the early stages, subduction formed an oceanic arc known as the Woyla Arc and accretionary complex. During the mid-Cretaceous, this arc was accreted to Sundaland, causing thrusting, regional metamorphism, and granitic intrusion. But the main tectonic control is oblique subduction, which produced both compressional and strike-slip deformation. In the Cenozoic, the system was reactivated and formed the Barisan Mountain and the Sumatran Fault Zone. So, this belt is very important because it records the tectonic evolution of Sundaland from subduction and accretion to later deformation.
Moving on to the last part of our discussion, we're going to talk about the regional significance, as in why is it important for us to understand the geology of Sumatra. That's why we're going to talk about 4 key aspects that we need to understand. First thing first, the crustal evolution. Sumatra records the transition from oceanic to continental crust through accretion, subduction, and also magmatism, forming the metamorphic rocks such as schist and gneiss, and also the S-type granites. Secondly, mineral potential. These same processes generate important resources such as gold, copper, tin, and even the geothermal systems. Thirdly, the tectonic reconstruction. Sumatra helps explain how Southeast Asia formed, especially through terrain accretion like the Woyla Arc collision, and also the development of oblique subduction and the Sumatran Fault. And lastly, number 4, the geohazard implications. These active systems produce both megatrusts and also the shallow earthquakes, making Sumatra highly prone to natural hazards. And overall, the Sumatra is regionally significant because it records the geological evolution while directly controlling the present-day hazards and also the mineral resources.